about 100 years ago, when the first geologists come to the Flinders Ranges, looked at these rocks and saw the evidence for sediments that were deposited by melting ice, they asked themselves a question: how could you have had ice that formed part of the Australian continent when Australia is so far from either the North Pole or the South Pole? As we see today, this is a warm climate. And yet you have evidence of ice here. And at the time that they found this, no one knew that the continents could move. So they actually reported this to geologists in Europe, who made trips to Australia just to study the evidence for this very ancient ice age. They knew these rocks are old, they didn't know how old, but they knew they must predate, be much older than any other recorded ice ages of that time. And more the point is, people began to find similar evidence on other continents. So it's found in almost every continent on the globe. And yet most of those continents are well away from either the North or the South Pole today. So something had changed. Now, since then, in the last 50 years, we've learned that the continents can move. It used to be called continental drift, and now we call it plate tectonics. We have a mechanism whereby the continents can move around slowly on the crust of the Earth, and so continents can break up and they can amalgamate again. And so for a long time, we forgot about this anomaly, that here are rocks which are clearly deposited by melting glaciers, but they occur at about 30 degrees latitude. Nowhere near any ice sheets that we know of today except mountain glaciers, and these clearly weren't deposited by mountain glaciers. But some new evidence turned up when geologists began to drill into these rocks and take core samples and examine the fossil magnetism in the rocks. You'll notice these rocks are red. That means they've got grains of iron mineral in them, hematite in particular, and a version of hematite that actually preserves a little magnetic field. So if you think about the trick that you do at school, where you put a magnet under a sheet of paper and you sprinkle iron filings on it, those iron filings line up in a very characteristic pattern. I'm sure you've all seen a bar magnet with the iron filings forming great curves out of the top of the bar magnet and coming back to the bottom of the bar magnet. We call that a magnetic field. So somebody had the idea that if it happens with iron filings, it should be happening on the Earth today, because the Earth has at its core a dynamo which is very much like a bar magnet, and we know that a compass roughly points north when you're at the surface, no matter where you are on the surface of the Earth. And you also notice that as you go towards the poles, the magnetic field seems to plunge into the Earth, and so when you're at the North Pole, it appears to plunge directly in and out of the Earth, and at the South Pole directly in and out of the Earth. So it's normal or perpendicular to the surface of the Earth. Conversely, when you're near the equator, the magnetic field is pretty much parallel to the Earth's surface. So the trick is to take pieces of core and carefully orient them and then unfold the rocks. In other words, take the tilt out of the core and work out what orientation the core had when it was originally mud on the seafloor. Because in that mud there are particles of iron minerals which would have lined up just like iron filings do with the Earth's magnetic field. And so it's a kind of a fossil magnetism preserved in rocks like this.